Okay, so 10 data, 10 output data you have to have it. And also use 12 to 16 significant digits for the filter coefficients so that your output data will be accurate. Okay, and also the freedom of the significant freedom in the design process. So you must decide your objective in filtering the signal before you start that. That's what I was telling, depending on the application. Okay, guys. So now let's continue with some more examples here. Okay. So now you have seen that FIR filter output is IIR filter. This is an IIR filter. Okay. This is the signal. Okay. Y of n, that is x of 0.5 x of n. So this is a coefficient that will be given. Okay. And also the same range y of n, that is the 136, the value for the y of n. Y of if you can move fast, I can complete the analog filter. 3 problems are there in the analog filter also. Can you tell me the value for the y of n? One.
1.5.
The first one is 1.5. And the second data
4.5.
4.5.
It's the brand new iPhone.
Yes. Third one. How much? 7.5. You can add more significant digits, okay? So it should be, as I told you just now, in the especially for the IIR filters, you can have more significant digits, 3 or 4. They recommend you to have in the real computation 12 to 16 significant digits. Okay, at least for your calculator you can have 3 or 4 for your exam also. So for the data,
Shouldn't the second one be 3
okay.
plus?
So you are clear
Like
how to
7.5.
calculate the values for the y of n. Let me proceed. Okay. So first value is a 1.5. Second is 3.75. It is not 4.5. Okay. And y of 2, that is 6.375. Okay. And the y of 3 is 9.1875. And for the fourth data, it's 12.05. So now you can see that y of n, okay, for the given data 3, 6, compare, just make it compare. The FIR, you can see the 1 here, it is 1.5, it is 12 here and 12 point. For the data 15, it will be 12 and 12.095. So this IIR pretend to be more accurate, closer to the real value compared to the FIR. Now let us see. Okay, before going to the practical example, let us identify the examples here. That is, this is the digital filter here. Okay. What is is it a recursive or a non-recursive one? Maybe it's very simple, but expected multiple choice questions or small answer questions in the exam. No? Is it a recursive or a non-recursive one? It's a recursive. Why do you say? It is y, the input, the feedback input y of k minus 1 is there. So this is a recursive one. Is it in FIR or IIR? IIR or FIR? IIR. So it is a recursive one and it is a IIR. What is this one? Non-recursive one, okay? Why? Because only the x of input, x of k minus 1, x of k minus 2 up to x of k minus n is there. So it should be a non-recursive one.
You know,
Just to recollect
I
your
was also like,
remember memory,
the other one I'm
recursive
talking
filters,
about,
okay? They
there's
have
a
addition to the
Oscar when
current,
he
the
filmed
past
the one,
input
and it was
values
just
are
part
there.
by part,
In the
and people just made fun of
non-recursive
the
one,
name.
only the past input values are given, okay? And the FIR is the no feedback, and IAR have the feedback. Okay, guys? Are you clear? Okay? Okay, now let's go for a simple temperature sensor, okay? And let us see that how effective it is in smoothing the curve for the or removing the noisy signals in your sensor data. Okay, so now you are using a temperature sensor with noisy readings, and now I need to smooth this signal using my FIIR filter. Okay, I need to smoothen this one using my IIR filter. This is the equation.
Today at 2 p.m.
That is the function y of n.
Mike, you're dead.
So the coefficients are given here 0.8 y of n minus 1. And the input from my sensor, the temperature sensor is varying from 30 to, you can see that 30, 29. So my input is varying from plus or minus 3. Either it is the Fahrenheit or degree Celsius or anything, we are not worried about that, but the data are this one. Okay, and this y of minus 1 that is given as a 30, that is the, to start with, the initial data you are given as a 30. Now, can you smooth this temperature from y of 0 to y of 4? That is, what is the value for y of 0, y of 1, y of 2, y of 4, like that. So what is the value for the y of 0 to y of 4? This is the IIR filter, and given the function is given there.
Go backwards by any chance?
Huh?
Can you give me the y of 0, the first value? For 30? What is the value for 30?
It's 30.
It is 30 itself? Okay. Let's see. For the second one, the decimals, don't forget the decimals, okay? Decimals are important in the digital filters.
So how does it change from sequence to sequence though?
That's you're saying like
The second data, 32.
back and forth. How did they change?
Why is it like as you're shifting from data set?
So this is 3.00, sorry, 30.00.
Power series approximation, but I don't get where the coefficients come from.
And the second data for 32. 30.4. Then for the third data for 29. 30.12. Then the fourth data for 31. 30.206, 30.96. Then the final data.
30.296.
Or 296, 30.296. Come on guys, from the other side, here. What is the final data for the 30? Any other values? 30 point? Can you come again? 368? 668. Okay. Can you just compare the input data? Okay. So now I have the values for 30, 30.4, 30.12, 30. So for my input, okay, for my input of x of n equal to the previous data, that is a 30, 32, 29, 30, 32, 29, okay, then the 31 and 30, 31 and 30, okay, x of n. You see how my input data is smoothened, okay. This from here you can see that I have a variation of plus or minus 3 degrees Celsius, but here after using my digital filter I have less than 1 as a variation. So this is the practical application of your digital filters. Can you understand the previous calculation what you did and the calculation what you did on the practical application? So there you practice how to calculate the n, that is the x of n and y of n, and if you are given a real data for a temperature sensor, you can smoothen your curve, okay, smoothen your curve, and you are going to get a minimum of ESR. Okay. So now what happens here? The filter smoothens the noisy readings, okay, but preserving the data itself. Okay. So now similarly you can apply for an audio echo effect. Okay. So this is another filter, okay. So this is an IIR filter, x of n, y of n is given. So it should be an IIR filter, okay. Now this is the function given here for a data of 10000 here, and the y of n, the previous input value, that is given y of n equal to 0. So if you calculate it, you're going to get the value for this one as 1, for 0 it is 0.6, and for the third data it is 0.36, for fourth data it is 0.216, and what you can observe here is it mimics the sound and echoes and fades. In your digital filter, what happens if you are giving a data of 10000, you are going to get the digital output of 1.6, 0.36, 0.216. So it is nothing but it is a echoing of this one, okay, and then it fades away. Okay, so this is the effect of this digital filters. So I have given some more examples. You can plot the graph and see using an Excel or Python or any other data. You can have it later, okay? And I'm going to post these slides in the cameras. You can do that later. Now let me pass on to the next topic, another 20 minutes for the analog filters, the problems. Let's work out 3 or 4 more problems in this one. So just to refresh your mind, what is the analog filter? So if your input signal, okay, if your input signal is x of t, that is a sin omega t, what is the nature of the output you should have? What should be the nature of the output after this analog filter? Yes, the phase shift should be there, and also the amplitude will change. Remember? So the previous class I gave you the formulas, okay? The phase shift will be there and the amplitude will be changing. Here you will be having a phase shift of phi. So y of t, okay, that should be b sin omega t, okay? And also remember that if it is a sine wave, okay, you have sinusoidal wave, you will have the sinusoidal wave. If it is a cosine wave, you will be having the cosine wave as the output, but the amplitude and the phi will be changing. Okay, and you know this is a simple RC circuit, the transfer function of an RC circuit. Okay, and now for this one, how do you calculate the amplitude and the magnitude? So the magnitude and the phase angle. So these are the formulas: V out by V in. That is the real part, root of A squared plus B squared. Okay, the real and the imaginary part. Okay, and the input real and the imaginary part, and you can just simplify it to get this function. That is the magnitude, and the phase angle phi. That's nothing but tan inverse of imaginary by the real part minus the denominator here, tan inverse of j omega, that's tau omega by 1. So you will be getting, so these are the two formulas you have to remember, recollect it, because we are going to use it for the problems to solve here. Now, read the problem, discuss with your teammates there, and find the output signal V out of t. So you are given a sinusoidal wave, a cosine wave here, okay? V in, that is 6 cos 7t, and the filter transfer function that is given by V out by V in by this formula, okay? Determine the harmonic output signal V out. Just now I told you, what are the things you have to calculate? Amplitude is going to change, okay? So the V out, so now you are having V in of t, that is equal to 6 cos 7t, that is a cos omega t here, omega the angular frequency is 7, okay? And then V out should be V out of t, that should be, the amplitude is going to change, okay? This is going to be B, and cos of, okay, here 7t, so omega t, so that's going to change 7t plus 5. So this is how I need to have my final equation, okay? Do you agree? Now you have to calculate the value for the B and calculate the value for the phi from this equation. Am I clear, guys? Is it okay? Any doubts? Okay. Now can you proceed and tell me the values? So what is the first step I have to do? Now the values are given, okay? The values are given. Resistance, inductance, capacitance, and values for a frequency, the radial, the frequency, angular frequency omega, that is 7 radians per second is given. What is my first step? Yes?
I would think like you could potentially have a direction V out function by multiplying the V in out of this and just keeping that 6 cosine of t. But if we want to change the trig function and like do the phase shift and such, my best bet would be to put it to both the magnitude and phase versions and work from there.
So the first step, you need to plug in the values, no? The values for the R, C, everything, and get the complex number, okay? The transfer function in terms of a complex number, the J, without the R, C, L values, okay? Do you agree, guys? Okay. So now I have my complex function in terms of the numbers, okay? I have only the J here. So this is a complex number. Now, from your practice of your previous complex numbers, you know how to calculate the magnitude and the phase angle. Okay? So the magnitude, you know that the root of A squared plus B squared, okay? The real part square plus the imaginary part square of the numerator and of the denominator. Do you agree? Okay, I have to speed up a little bit. So now, the phase angle, the first thing, the phase angle phi. Can you get this one? Calculate it. At least try to calculate. Give me the value. The phase angle. Give me the value for the phase angle. Negative? 2 point. So you'll be getting negative 2.941 radians. Are you getting guys? Any difficulty in this? Will there be any difficulty in calculating the phase angle phi? Okay, now can you calculate the magnitude? Can you calculate the magnitude? That is, as I told you, this 6, it's not going to remain the same. Okay, this is going to be multiplied by another factor there. Okay, so can you calculate that magnitude here? This 6. It's going to change, definitely, using the formula root of real part square by imaginary part square divided by the denominator there, root of real part versus the imaginary part, the square root of that one. Yes. It's in the radians there, so no harm in that. Tan inverse of 33.6 divided by negative 0.7. What is it you're getting? Okay, this takes the same process. Yeah. Are you getting 2.941? No, you're getting 2.9.
Negative 0.
Yeah,
You guys get the right
2.0
number?
something. 2.0, not 0.
Yeah, I did.
This one is 0.2.
Yeah.
In terms of rating.
Yeah, I got that too. Yeah, I'm negative these.
Okay.
And then you had another negative.
Okay, let's take it. So you have, I don't know, your calculators or any other mistake, let's check it later, okay? But the methodology is more important. Now, the magnitude. The magnitude here,
Oh, I don't.
at least, are you getting this value, 0.02?
Why'd you divide, like, you divide it through,
Okay.
like, 3.6?
So now, how to write my
Because that's
equation,
the
final
original
equation?
And then it got split into a
How to write
subtraction.
my final equation now? Is it okay now, writing like this? We have t, that is the k, the constant, okay? So now, you have to write your equation b out of t, okay? Out t that is equal to, and in your exam, try to highlight this one, because this is going to be your final result, which will be graded by the TAs, okay? So this corresponds to k, okay? That is nothing but 0.0123, okay? And this 7t, okay? That is the omega equal to 7 minus 2.941, okay? So this is going to be your final result. Okay, now let's pass on to the next example. From our previous knowledge, you know that if we are having a signal which is composed of 10 Hertz and 15 Hertz sines, sinusoidal waves, then we can write, okay, y in, this is the input signal, y in, that is sine 25t, okay, plus sine 35t, okay. I'm writing in terms of the frequency here, okay, hertz frequency, okay. Now, let us assume that this y in of t is the voltage signal, okay, where 10 hertz sine wave is the desired signal, and this 15 hertz, the second one, is an undesirable noise. Okay, now let us try to reduce the amplitude of the noise using a basic low pass RC filter. Okay, and the transfer function that's given by this equation, V out by Vs, that is 1 by 1 plus RCS, where S, you know, that is a complex number, J omega. Okay, now determine the equation for the output signal Y out
Did you say 0 or
for
G?
different cutoff frequencies, okay? So the cutoff frequency that's given by 1 by 2 pi RC for 1 hertz, 10 hertz, 15 hertz, and 100 hertz, and you have to compare. Yes.
What can you write out what S means? I didn't catch it.
Which one? Yes.
S, yeah.
That is the J omega. That is the complex number.
J omega. Okay.
Yeah.
J omega. Okay.
So this
J
one,
omega.
this S will be the J omega.
That's not what it sounded like he said.
How can I proceed, guys?
Right. Let's see. Okay.
So now, read the problem carefully. So this is the sort of question what you may get in the exams, okay? Because there's only 4 frequencies you can easily calculate using your calculator. You're not supposed to use any Excel or any programs to calculate it. So only these sort of simple questions will be there, okay, in the exam. So now you are going to have, okay, say for example, you are going to have y in, okay, of t, that is sine 20 pi t plus 2 sine 30 pi t, okay. What will be my y out of t? That should be, there should be a change in the amplitude. Do you agree? There will be a change in the amplitude. So I'll put the amplitude as A1 and sine 20 pi t plus phi 1, the phase change for my desired signal, that is the 10 hertz signal. Then the second term, this will be again plus A2. I don't need to write the input the twice. Mind that another hint is given here. Your noise signal is twice that of your desired signal. It's a heavy one. Okay. So suppressing with the filter, you are going to see the result. What is it going to have? So A2 into sine 30 pi t plus phi 2. Can I write like this? So my output should have A1, phi 1, A2 and phi 2. So now
Why did that
your
two
task
disappear
is
then?
to calculate all these values of A1, phi 1, A2, phi 2 and
It's-
plug in the values here and write the final equation for
The new equation
1
is different
hertz,
than the
for
two,
10
than the
hertz,
original
for
one.
15 hertz
So,
and
The
100
two
hertz.
will probably come into play
You got it.
to calculate it, but
Did you got it, guys?
it's because they have different.
So you are going to have 4 equations, okay? You are going to have 4 equations for 1 hertz, 10 hertz, 15 hertz and 100 hertz, okay? For the input frequencies of the sine 20 pi t and the sine 30 pi t. Can you do it? Can you calculate the values for the A1, A2 for different frequencies, cutoff frequencies, okay? 1, 10, 15 and 100 for A1 and the phi 1, A2 and the phi 1. Okay, let me walk you through. So this is a simple RC low pass filter, okay? And you know that y out by y in, that is a transfer function, okay? That is 1 by RCS, okay? And the cutoff frequency is 1 by 2 pi RC for 1, 10, 15 and 100 hertz. Okay? Now, you, as I told you, you should have 4 values of FC, the cutoff frequencies, and Y out also will be a compound of these 4 values with the two sine waves. That is a 10 hertz and the 15 hertz signals, or the angular frequencies of 20 and 30. Okay? So now I write my output waveform, the required output waveform. It should be like this, as I told you. Now my task is too easy to find A1, Pi1, A2 and Pi2. Are you good, guys? Is it okay? Now how can I proceed? So now I have to calculate the cutoff frequencies, that is a F cutoff, or in terms of the RC, I'll plug in the value in terms of the RC, because now I know the RC here, okay? So I'll convert this cutoff frequencies in terms of the RC, and the Y out by Y in, the transfer function here, I can replace this RC with this RC here. So S by 2 pi F cutoff frequency. Now I can vary this cutoff frequencies for 1, 5, what is the value given? 1, 3, 5, 10, something like that. 1, 10, 15, 100 hertz. Okay. So now I know that yes, that is the I omega or the j omega. Okay, and omega is going to be the angular frequencies 20 and 30 pi. Okay, for the 2 sine waves. So now I can replace Y out in this formula, that is I omega by, so this omega I'll substitute the values for 20 and 30. So for the 10 hertz I'll be having this, okay, the transfer function, and for the 15 hertz I'll be having this one. Okay, so now this is for the 10 hertz. I need to find A1 phi 1 and I need to find the A2 phi 2 for the 15 hertz. Okay, so now I'll calculate the gain Y out by Y in. So 1 by root of A squared plus B squared. This is the real part plus the imaginary part squared. Okay, so 1 plus 10 by FC whole squared. Here for the 15 hertz signal, this one. But be careful, A2, as I told you in the beginning, it is the sine wave of twice the magnitude of this, the initial one. So now the value for the A2 will be 2 by 1 plus root of 1 plus 15 by FC whole squared. Okay. So now the phase angle now for the 10 hertz will be like this. This is 0, tan inverse of 10 by FC, and this is the negative tan inverse of the 15 by FC. Can you guys follow the steps? Okay, are you good? Okay, now I can plug in the values for the omega, that is the FC, the cutoff frequencies, and I can have the values for the A1, I1 using your calculators. You can do it, and you can tabulate the A1, pi 1, A2 and pi 2 values corresponding for the 4 cutoff frequencies of 1 hertz, 10 hertz, 15 hertz and 100 hertz. Once if you find the values for the A1, pi 1, A2, pi 2, then you can easily plug in those equations. Okay, this is nothing but, so this is nothing but A1, okay, sine 20 phi, okay, t minus the phase angle phi 1, okay, and this is plus A2 sine, okay, 30 pi t plus minus phi. So these are the 4 equations you will be having it, okay, and if you plot it in the Excel, you are going to see that the signals are significantly attenuated, okay, and shifted when it is at the 1 hertz. It gets attenuated, attenuated. It is reduced, almost suppressed, okay. And for f equal to 100 hertz, you can see that the signal that is the input signal, and the output signal will be close. It will be having the sinusoidal wave almost overlapping to each other. Okay. So once if you plot it, you can visualize. Or from the values, you can give some theoretical interpretations in your. Now, based on these same frequencies, okay, the four filters with the cutoff frequencies of 1, 10, 15, and 100 hertz. Okay. Determine the reduction in the output power of this 10 and 15 hertz. So you know the power reduction that's given by in the decibels 20 log V out by V in. Okay. So now for this 10 and 15, you can have the power reductions. Okay, that is A1 by 1 and A2 by 2, and you can calculate for the 1 hertz, 10 hertz. So plug in the values for the A1, A2, okay, you'll be having the power reduction for the 10 hertz signal like this and 15 hertz signal like this. Okay. And the next one, this is more important. How are you going to reduce the signal to noise ratios? That is, you know, 4 filter cutoff frequencies and determine the signal to noise ratio SNR, that to expressed in the decibels. Okay. So now we know that SNR will be defined as a 10 hertz power divided by the noise signal to noise ratio. Okay. So 15 hertz is the noise. Just I'll walk you through this one, have an idea. So now the SNR is nothing but the same formula, the power formula, but the Y in by the, that is the input signal to the noise signal, okay, or desired signal to the noise signal, okay, and SNR will be, for the input signal it is 6.02 decibels, but if you plug in the values for the A1, A2, the A1, A2, 51, 52, which calculated in the previous table, you are going to get the SNR value for 1 hertz as 2.52, 10 hertz 3.9. See now compare this one. Compare the input, okay, in the input noise to the original, the desired signal to the noise ratio is double, 2 times the sin 30 pi t, okay. So that is 6.02 decibel, but after the filter you can see that for 1 hertz it is significantly suppressed to 2.52 decibels, but 100 hertz, as I told you, so if you draw the waveform for the 1 hertz, okay, it will be, the signal will be suppressed, but for the 100 hertz, the signal as well as the noise signal, okay, the noise signal will be the same, but for this one it will be suppressed with the same frequency. Okay, so 2.52 the signal to noise ratio for the 1 hertz, and for the 100 hertz it is 5.7. Okay, so these slides I can post it, okay, today, and you can have a look at it. And Monday you'll be having a revision of the whole exam, okay, from the examination point of view. What is the pattern of the exam? Some problems.
Oh man, I hope the majority of the last exam